In today's class, we'll look at the different types of quantities and other areas of measurement. Remember, in the previous class, I told us that quantities are actually measured observations. Yes, when you have an observation and you ascribe a numerical value to these observations, we refer to them as quantities. We have fundamental, now, as the name implies, fundamental quantities. Can you remember when we defined cell as the fundamental unit of life? There's also another definition of cell being the basic structural and functional unit of life. Yes, it means that every living organism consists of cell, or we could say that for there to be life, there must be a cell. This means that anything that's pertaining to life have its roots stemming from cells. If something is regarded to be a fundamental, it means it is the basic or the simplest unit of that particular substance. Now, we have that there are fundamental and derived quantities in measuring observations, and these fundamental quantities are the simplest or the basic quantities upon which other quantities can be derived. If I have a fundamental quantity or a basic substance, it means I can as well get other substances from either the combination of these simple or basic substances. That being said, we have fundamental quantities to be quantities like mass. Remember when we discussed in our previous lecture that these quantities are measured using tools for effectiveness, and then these tools are graduated and are measured in units. So the unit of mass, if you could recall, is what? Kilogram. And another fundamental quantity we have is length. In measuring length, we use meters. So we could say the unit for length is meters. And the third basic fundamental quantity is time, which is measured in seconds. Looking at these units, kilogram represented as kg, length in meters represented as m, and time in seconds represented as s. These three are the basic or fundamental units of measurement that are also referred to as the fundamental quantities. Recall the definition of mass to be the amount of material or substance contained in a body or an object, and time to be the sequence or progressiveness of series of events ranging from the past to the present. And we have for length to be the distance covered, or the distance from one point, let's say A, to another point B on a particular object. Now, we have these three to be the basic or fundamental quantities. Although there are other quantities we could also call fundamental quantities, but these quantities measure some very important aspects of chemistry. When you want to measure very minute substances, when it comes to the amount of particles in a body, we say that is the mole. So if you want to measure the amount of substance in a body, we consider that to be the mole. And so in measuring the amount of substance, we have its unit to be mole. Another fundamental quantity is also current. In measuring the amount of current that flows through a wire during the conduction of electricity, we measure that amount of current in amperes, which is represented as A. There are other fundamental quantities. I think there are about 7 of them, but these few I've been able to give to us are likely to be used in certain calculations in chemistry. Now, if we have fundamental quantities, does it mean the combination of those quantities could actually give us other quantities? Yes, of course. That's where we have the derived quantities. So, these derived quantities are gotten from a combination of fundamental quantities. And we could say that derived quantities are dependent or are gotten from the basic quantities, which are mass, length, and time. Let's take, for instance, say we have a derived quantity, volume. Now, from the definition of this derived quantity, remember that these quantities are barely measured observations. So if we have volume, you see that volume is the amount of space a body occupies. Remember, we define matter to be that object or substance that has mass and can occupy space. So if I want to measure the amount of space a particular object occupies, we will say that quantity is referred to as volume. So in terms of measurement as regarding volume, we have that to be able to measure the amount of space, we measure the total size of that particular object. Remember when we used the measurement, or when we calculated area to be length times breadth, or for objects that do not have a breadth, we say length times length. But in the case of a three-dimensional shape, we look at length times length times length. So instead of having a length times a breadth times a height, we have length times length times length. Can you remember the units for measuring length? Yes, of course. The unit for measuring length is meters. So we have meters times meters times meters. And this gives us a cubic form. So we have that volume is measured in meter cube. Can you see that this derived quantity volume was actually gotten from the fundamental quantity length, same as its units? From this, we could say that derived units or units of derived quantities are gotten from fundamental quantities, or units of derived quantities are gotten from fundamental units. Let's take another example. For instance, we have density, and we define the density of an object to be the mass per unit volume. We are taking cognizance of the fact that it has a mass and then it has a volume. So we want to know the total weight or heaviness of that particular object. So we have that density is mass over volume. Remember, mass is a fundamental quantity. Yes. And could you remember the formula we used for volume? Yes, of course. Looking at the example above, we said that volume is simply taking the length of that particular shape, the total length. We have meter cube coming from the L cube. If we're looking at the derived quantity, density, which is defined as mass per unit volume, or mass all over volume, we say mass measured in the unit kilogram all over volume, which we already have as meter cube. Since this is a derived quantity, you could as well see that its unit is derived from the fundamental unit. So we have kilogram and then we have meter cube. According to the law of indices, division could simply or could also be represented as a what? A minus, right? So if you have kilogram per meter cube, we could also say with a minus sign, which simply shows or tells us that the relationship between the mass and the volume is a division. In getting the density of a body, we're going to divide the mass by the volume. In expressing velocity, a derived quantity, we observe that when a force is applied, it moves a particular distance and at a particular speed, or would use at a particular velocity. This body, when force is being applied, moves a distance per time. We're looking at 8 meters in 1 second. Remember, meters measures length and seconds measures time. Remember the definition of time to be the progression of events as related to the past and the present. So we have that velocity is the displacement, because displacement is a vector quantity, it has a direction. So we say that velocity is displacement per time. And displacement is almost same as distance. The only difference is that while displacement has a direction, making it a vector quantity, distance has no direction, making it a scalar quantity. Having displacement and time which is measured in seconds. Remember I said displacement is invariably distance, so it's measured in meters, which is m, and then we have time which is measured in seconds, s. Remember I said that a division sign according to indices could mean a minus. So when I have meter per second, I could simply say ms m/s or ms minus 1. So this minus 1 simply shows that the meters is in division to the time in seconds. Now, if we're going to take another example, say acceleration. What is acceleration? It discovers that the distance moved in a particular second differs per second as well. So I can move in a second a particular distance. We have to define acceleration as the velocity per time. When a distance is moved in 1 second, what is the distance moved in a second when that particular body is in a particular second? So we have that acceleration is velocity per time, where velocity is already distance moved per time. So we have acceleration to be velocity over time. In deriving the units for acceleration, because we already have a definition of this term, remember you must know the definition of a particular quantity for you to be able to deduct or deduce its units from this definition. So if we know that acceleration is velocity per time, and already we established that velocity is distance per time. So each unit is meter per second. So we simply impute the units for velocity, which is meter per second. And then we have our time to be measured in seconds. We have that acceleration is meter per second per what second. Remember when I told us that we could use a minus sign to display the division. Now we have meter no longer per, so we're not using the division sign. Using the principle of indices, we have s raised to the power of minus 2. Why? We have two quantity of time. So we have one s and we have another s. According to indices, when you say s plus s, you simply add up the powers of those quantities. So every individual quantity has a power of 1, except otherwise stated. So if I have s having a power of 2, that means s is actually 2. But if s is standing alone, it is assumed, in fact, it is known that s is raised to power 1, since it's a single property or a single quantity. So if I have 2s, I would say s raised to power 1 plus s raised to power 1, which gives us s raised to power 2. And according to the law of indices, when I have a minus sign, because the division shows a minus sign, so we have s minus 1 plus s raised to power minus 1, which will give us s raised to power minus 2. So this gives us the units of acceleration to be meter per second square. These are units, derived units, and I've shown how these derived units are gotten from fundamental units. Do you remember the other units I talked about, the fundamental unit? Mole. Yes, mole actually is used in measuring the amount of particles in a substance. In chemistry, when we look at the reactions or what happens in matter down to its basic, where we consider the atoms, we mostly deal with measurements in moles. We could say that an amount of substance is measured in moles. Now, molarity being the amount of solute in a solution. The solute in a solution. So simply solute all over solution, because you could say that these solutes are measured in moles. These solutes are the amount of substances. They could be very, very tiny. So we're going to use moles. So for the solutes, we have them measured in moles. While for the solution, we have the solution measured as a volume. Remember, these solutions are simply liquid. And if you can recall, in one of our lessons, we gave the characteristics of liquid to be substances that can flow. And these substances also assume the shape of the container. We cannot literally measure the mass or the volume of this liquid, except they are being put into a container and they're measured as volume. Remember, we used meter cube as the unit for measuring volume. But in the case of molarity, the volume here is measured in decimeter cube, or we say cubic decimeter, which is dm cube. You should be wondering, I mentioned earlier that volume is measured in meter cube. So how come I have a decimeter when I was talking about volume under molarity? Now, we're going to look at what we call the metric system of units. The metric system of units. You should be wondering by now, I thought we're done with units. Not yet, because we need to understand that there are certain substances that are too small to be measured, and there are others that are too large to be measured in numbers. So scientists had to come to a point where they get approximate values in forms of decimals in order to make measurements easier. For instance, if I want to say 10 million, which is 10 and 60, I could simply say in decimal form to be 10 raised to the power of 6. Now, this 6 in the metric system of measurements is regarded to be what we call a prefix. We use a prefix to define or describe the 6 because we had to compress this particular value. Now, we have a table for the metric system of measurements. And this table consists of measurements or prefixes for measuring very minute quantity of substances, and as well very large quantities of substances. Let's look at the table where we have the metric, that is the measurement, and we have the prefixes. We have for 10 raised to the power of -1 to be deci. We have 10 raised to the power of -2 to be centi. We have 10 raised to the power of -3 to be milli. We have 10 raised to the power of -6 to be micro. We have 10 raised to the power of -9 to be nano. We have 10 raised to the power of -12 to be pico. We also have 10 raised to the power of -15 to be femto. And we have that for 10 raised to the power of -18 to be atto. And it goes on and on. Now, this is in measuring very little and minute substances, or taking little measurements of substances. When we have all these minus, you could see things like 0.0000000 to infinity. Now, in measuring large substances, we have 10 raised to the power 1 to be deca. We have 10 raised to the power 2 to be hectare or hecto. We have 10 raised to the power 3 to be kilo. We have 10 raised to the power 6 to be mega. This is just an extracted table from the main table of the metric system. So you could just have these at the tip of your fingers in your memory to be able to aid you in calculations as well as measurements in chemistry. Now, remember I said this table was brought about or was discovered in the bid to measure very minute and very large substances. We're going to look at another concept of measurement where scientists, in the bid to aid communication between two individuals at different locations, had to come about what we call the conversion factor. Now, the conversion factor is used to convert one unit of a particular quantity to another unit. Remember, we discussed of how measurement was done in the ancient times using ancient methods, as well as using the conversion method in the modern times where we use measuring tools. These conversion factors help us to interchange or convert from one particular unit to another. For instance, we say some goods were imported from China and these goods were measured in pounds. Down here in Nigeria, after I've gotten my goods, I really want to cross check. I really want to ascertain and know exactly if these goods is equivalent to the amount that was or described by the exporter. I would do so using conversion factors. So if I'm not familiar with pounds as a unit of measurement for mass, I would use any other unit I am very convenient with. So that brings us to the concept of conversion factors. Now, if I want to measure that same mass of substance in Nigeria using another unit of measurement in mass that I'm convenient with, let's say kilogram, simply all I have to do is convert or change the unit of measurement that was used in Japan down to the unit of measurement I'm convenient with here in Nigeria. This brings us to what conversion factors are. Conversion factors simply shows the relationship between two units of same quantity. For instance, I gave the example of having a measurement of mass in Japan to be in pounds and having same measurement in mass of that particular substance here in Nigeria to be in kilograms. How do I correlate these two different units but of same quantity? We have a table of listed conversion factors, and I'm going to give us just a few of them. Most times, this table of conversion factors come in relating a particular unit of measurement to one unit of the other measurement. For instance, this is what I mean. I know we're familiar with this measurement of time where we say 60 seconds make 1 minute, 60 minutes make 1 hour. Yes, that is actually a conversion factor. So we could convert from seconds to hours. We have that 1 minute equals 60 seconds. We have that 1 kilogram equals 1000 grams. We also have that 1 meter equals 100 centimeters. We also have that 1 pound equal 453.6 grams. We also have that 1 inch equal 2.54 centimeter. This means if I have a particular quantity measured in a particular unit, I can change from that unit to another unit. Let's take, for example, I want to measure a particular tuber of yam of 20 inches in Japan was exported down to Nigeria, and I really want to know what length this tuber of yam is. in centimeter. Remember, the unit we are considering is from inches to centimeter. I'm going to convert 20 inches to centimeter. Using my conversion factor, which of these conversion factor suits my questions, or which of these conversion factors can actually help me solve my problem? Vividly, I could see that the conversion factor 1 inch is equal to 2.5 centimeter can actually help me solve this problem. So I would consider that 1 inch would give me 2.54 centimeter. Now, if 1 inch will give me 2.54 centimeter, how many centimeters? Of course, we don't know. It's an unknown, so we refer to it as x. Let's see. How many centimeters, let's say x, would give me 20 inches? What you simply do here is to cross multiply. You cross multiply, and this gives us x, of course the unknown, times 1 inch, which is equal to, we have 2.54 centimeter times 20 inches. Looking at this, we just have to take off these inches, leaving the centimeter alone, because we're actually looking for the length of that particular substance in centimeter. So we need the unknown to stand alone. So what do? We divide both sides by 1 inch. Now, 1 inch will cancel out 1 inch, leaving alone our x in centimeters, which is practically the unknown, while the units here will have inches cancelling outwards, inches, leaving behind my 20 alone. This gives us x, which is the unknown, in centimeter, to be, of course, anything divided by 1 is 1. So we have 2.54 times 20. Don't forget, in centimeter. This will give us 5.08 in centimeters. Now, one thing you should note is that in using these conversion factors, while multiplying the numbers, that is the values assigned to this particular quantity, you must carry along the units of these quantities in order not to misplace them. So for the easy conversion from one unit to another, you need to follow this process. So this has made measurements very, very easy. Whatever goods are measured in a different location, it could as well be gotten in equivalent in another unit based on the measurement of that same quantity. Haven't shown us how to use the conversion factors in converting from one unit to another while measuring the same quantity. I'd like us to look at another example so quickly. Remember, we said 60 seconds make 1 minute. So in 1 minute, we already achieved 60 seconds. can we actually calculate the number of 5 minutes in seconds? Yes, we can by using the conversion factor. 60 seconds giving us 1 minute. 5 minutes we are looking for how many seconds we could get in 5 minutes. Then what is the unknown? Of course, the unknown is the unit in seconds. So we have that our x giving us what? 5 minutes. We do not know our x. So what do? We cross multiply like I said earlier. Remember, in cross multiplication, you multiply the units alongside the values. This gives us x seconds times 1 minute equal 60 seconds times 5 minutes. Remember, we have to let the unknown to be alone. Yes, it's not known, so it doesn't have to mix up with the known substances in order to be identified. Since we're looking for number of seconds in 5 minutes, we're going to divide both sides by what? Yes, 1 minute. So we could cancel out the minutes. We now have our x in seconds to be, can you see there are like terms here? Of course, we have minutes and we have minutes. We have 1 minute and we have 5 minutes. So the minutes cancels out, leaving behind the seconds. So what happens here is we multiply 60 seconds by 5. And of course, 60 times 5 will give us 300. Now we have that in 5 minutes, we must have covered 3 seconds, must have covered a distance in 300 seconds. Can you see now that we have been able to convert the measurement of time from one of its units to another of its units? We have come to the end of this lesson, and if you have any question or any problem as regarding this lecture, you could kindly drop them in the comment section, as I'll be glad to attend to them. See you in our next class.